be.
Oh, there you go. It says
nice.
this meeting is being recorded.
Okay, cool.
Yeah, I'll find out where it's gone somehow. Yeah.
That sounds good. I'm guessing that it's probably going to upload it to some Zoom site somewhere, hopefully.
Right. And I'm sure about to track it down. Yeah.
So I think we better get those people in because it's
okay. Here we go.
Now.
Yep. Cool. I'll let them in now. Okay. So Karen McIver, John Burkett, Jennifer, Ron, Nathaniel.
Hi everyone. I've got a few people joining us.
Howdy ho, everyone.
There's people.
Hey. Good to see a few people.
Everyone's on mute.
Cool. Yes, once you all join, we'll ask you to put yourself on mute as we're doing the main presentation. But at the end, when there's time for questions, if you have any questions, you can either type them in the chat or you can unmute and just ask your question. Cool.
Yes.
Yeah, got a few people there. Okay. Hey, should we wait a bit more, or do you want to start us off, James? What do you think?
There's someone there. Good heart.
Yeah.
Good heart. It's to mute.
I can mute. There we go. I've done.
Cool.
Perfect.
Nice. Yeah. Oh, and it looks like Ron isn't on mute as well.
Hi, I'm here.
Hi. Hey, John. Good to see you.
Now, is Ron on mute?
We've got John and Little John. Cool.
I think we're all good to go.
Okay. Let's get going.
Let's rock and roll, guys.
Oh, welcome everyone to yet another lockdown edition of the Hibiscus Coast Astronomical Society meeting. So this evening we've got a pretty good talk about Mars. As you know, Mars has been in the news quite a lot recently. And of course, as we hear more about Elon Musk's plan of going to Mars, more and more we're getting information about that, amongst other things as well. So yeah, that's going to be quite an interesting one. So we're going to be starting off with Josh, who's going to do a very brief news segment before moving over to Chris. Yeah, thanks again everyone for joining us, and yeah, who knows when we'll be able to meet again, but our next meeting is 2 weeks time, and yeah, hopefully it shouldn't be too long after that, but we will see. So I think it'll be over to Josh for the news.
Cool. Thanks, James. Yeah, hi everyone. I'll start us off with some news, and we'll just do a short news segment tonight because Chris's talk about Mars is a bit longer than usual talks. I want to save time for that. So I'll just start by sharing my screen. Cool, that's in the way. Okay, cool. So let's get stuck into it. Astronomy news. What's been happening above us?
Actually, before you start, Ron, can you just turn your video off, please?
Yeah, thanks, James. Cool. So yeah, if you've been following the Inspiration 4 mission, this is the first all-civilian space crew. And this is quite exciting because we've had, you know, space tourism is quite a growing thing. But a lot of the recent space tourism flights, there's been at least one person on board who's, you know, a fully trained astronaut. The Inspiration 4 mission was different because all 4 of these people are just regular people. Mind you that they did undergo 6 months of training, so they didn't just kind of push them in the shuttle. But it was quite exciting to see these, four regular people like you and me undergoing this training and then going up into space in a SpaceX Dragon capsule. And they orbited the Earth for 3 days. While they were up there, they conducted experiments and they raised money for St. Jude Children's Research Hospital. So just a reminder, this whole mission is part of a fundraising thing to raise money for this research hospital. I believe they set the goal of 200 million, and last I checked, they'd raised 222 million, so they've exceeded that. They may raise even more because they said that the fundraising will continue into February in the next year. So part of that fundraising is things like, while they're up there in space, they took things up there, and now they're going to auction off some of those things. So if you're interested, you can buy something that's been into space. And if you're interested to know more about the story, I can definitely recommend you watch the Netflix series Countdown, Inspiration for Mission to Space. It's quite interesting just seeing this crew go through the training and then actually go into space, stay up there in space, try all the really cool things that we'd probably try if we got to space, like eating food in zero gravity. At one stage they had, it looked like M&Ms or something, and they were kind of throwing the M&M to, one of them would throw and the other one would kind of open their mouth and try to catch it. So yeah, very interesting seeing that all happening. And also in the space exploration news, Russia sends an actress and a movie producer to the International Space Station to shoot a movie in space. So the movie, it's an upcoming movie that will be released next year. It's called The Challenge, and it will be the first feature-length fiction film shot in space. So I'm sure a lot of us who are interested in astronomy are also interested in science fiction. But how cool would it be to watch a movie where the space scenes are actually filmed in space? So that will be quite exciting. And there's still talk that Tom Cruise at some stage wants to go to the International Space Station to film a movie as well. And that would be with the help of NASA and SpaceX. We don't have any firm details about that yet. It's still a bit under wraps. And for a while, it looked like that Tom Cruise might get there before the Russians. But it looks like in this instance, the Russians have beat the Americans in this, I guess, stage of the space race. So the Russians will be the first to film a feature-length movie in space. And this isn't going to be the first movie in space ever. This is just the first feature-length movie. Because back in 2012, there was a short movie called Apogee of Fear. It's only 8 minutes long, and it was filmed by a space tourist who was aboard the International Space Station. I haven't actually watched it myself. I'd be keen to find it. I saw just some still images of it, and it looks like the production quality is very low, as you might expect from something that people are just making with cameras. But, you know, it's still interesting. Whereas with the Russian movie, this will be interesting because it'll be the first, full feature-length, big-budget film with space scenes shot in space. And finally, in the news tonight, the Mars Ingenuity helicopter struggles with the change of season. So a lot of us right now might be struggling with the change of season through the allergies or hay fever or things like that. Well, Mars has seasons as well, and things change over time. And in particular, the seasonal changes at the moment are leading to a decreased atmospheric density. And so what that means for the helicopter is NASA needs to make some adjustments to how fast the blades spin to compensate for the difference in atmospheric density. So a few weeks ago, they planned to do the 14th flight of the Ingenuity helicopter, but it didn't get off the ground because the helicopter itself, before it starts flying, it kind of does a few test spins of the rotor and just measures that everything is looking okay. But this time things were a bit off. Some of the blades seemed a bit wobbly. So the helicopter itself made the decision, this doesn't seem right, I'm going to shut down. And so since then, NASA has been looking into it, trying to work out what's going on. They think they've solved it, and they think that they can update the helicopter to account for the difference in atmospheric density. but they won't be able to do that until after the Mars solar conjunction is over. So we're currently in the Mars solar conjunction, which means we can't talk to Mars. And this will stay in effect until later this month. And so just a reminder, what this means is, it means that if we're here on Earth, obviously Mars goes around the sun at a different rate. And at the moment, Mars is on the other side of the sun from us, which means that NASA can't talk to the rover. And for that matter, the Chinese Space Agency can't talk to the Chinese Mars craft as well. So yeah, hopefully in a few weeks that will open up again. And also with the Ingenuity helicopter, it's worth noting that this was originally just going to be a kind of a prototype test thing. And originally they were scheduled to do 5 flights, and that's it. But it's gone so well that they're now up to their 14th. So even though we're having a few technical difficulties with this last flight, it's worth keeping in mind that it's still doing really well for something that was only supposed to last 5 flights. And that's it for the news tonight. Very short news. And with all this talk about space exploration and Mars, once we finally get to Mars and land there, I'm sure one of the questions we'll all have is there water on Mars? So to help us answer that question, I'll pass over to Chris with our main talk this evening, liquid water on Mars. Thank you, Chris.
Just before Chris begins, if you've got any questions, you can put them in the chat, and we'll look at them at the end. Otherwise, we will give you an opportunity at the end to put on your video and audio and ask your questions in a regular fashion. So without further ado, just hand over to Chris.
Thank you. Thanks, James. Let's see if I can bring on this here to share. Can you guys see that?
Yep, all good.
Yes, all good.
Good. Play from the start. It's a good enough place to start, isn't it? Okay, guys, and I'm just going to flick this over to the side so I can see my slides. That's good. I think it's time to rock and roll. Welcome, everyone. Okay, I am just positioning my slides and getting rid of my, trying to minimize things here so I can see my own slides. No, I can't, but I'm not going to worry about that. We're just going to rock and roll and get moving. Okay, so what year is it? 2021 rather. So it's 50 years ago this year. It's the 50th anniversary of NASA's Mariner 9 spacecraft, which was the first craft to go around any other planet. And it went around planet Mars and it took these sort of grainy type pictures, images we got back. And it immediately got everyone's attention because what do you see? Those features look very, very suspicious for flowing fluid of sorts, most likely water. So everyone was instantly interested in Mars when those pictures came back. So of course we know a lot more about Mars now. So let's go exploring. Here's some recent pictures that have come back from rovers and landers that have landed on Mars now. Beautiful high definition pictures. As you can see, Mars is a very dry and barren place. There ain't no sign of any water to be seen around there. Thought, well, that's interesting. Then you look a little bit closer in some other areas and you think to yourself, oh, that looks dead dry and barren, but hang on a minute. There are some features there that you sometimes see on Earth, some very features that are very suspicious, like dry lake or river beds. And that immediately got everyone's attention. There's obviously more to Mars than we realize. And the thing about Mars, that sort of the whole mystery about water and so on and liquid water, is that Mars's atmosphere is very cold. Its average temperature is about -60 degrees. That's colder than a student flat in Dunedin in the middle of the winter. And it's also very thin. It's only about 1% the thickness of Earth's atmosphere. And of course, liquid water needs to be warm to stop it from freezing, and it needs a thick atmosphere to stop it from evaporating away. So instantly, we have a problem there. So the problem being Mars's cold, dry, and thin atmosphere is not suitable for liquid water. but we've seen some features on Mars that look very suspicious, like it's been there in the past. So the questions are, was there liquid water on the surface in the past? What changed? When did it change? And why did it change? And that's why tonight's talk is Liquid Water on Mars, a story of climate and change. And I'm just going to see if I can drop, I've got a whole thing sitting over my screen. No, I can't. I'm going to just keep going. Okay, so I've split it into 5 chapters. First of all, we'll talk about the current conditions on Mars. Then we're just going to briefly review some prominent relevant geological features which are relevant to this talk. And then we're going to present the evidence for past surface liquid water on Mars. Then we'll talk about the early atmosphere of Mars and its climate history and how they've worked that out. And then we'll sum up and conclude. So first of all, general conditions and the questions that are being debated. We'll talk about surface water. Then we'll talk about surface ice, I should say, subsurface ice. And then we're going to talk about 4 subglacial lakes underneath the glaciers that they can see. So this is pretty much summarizing what we've talked about so far. If there was liquid on Mars, if there was water on Mars, rather, was it liquid? Was it solid? Was it above the ground? Was it below the ground? And hey, where is the water now? What's happened to it? What was the climate like to have supported water, whether it be above the ground or below ground? And how about the climate? Why did the climate change? How did it change? And when did the climate change? So those are the key things that we're going to address tonight. So let's look at where there is surface water ice. And the bottom line is it's at both polar regions, the north and the south caps. And I've got myself a Mars globe here, which every home should have, along with some caps. So here's Mars, and where do you find some surface ice? 2 main areas: 1, North Polar Cap; 2, South Polar Cap. So yeah, both North and South Poles have ice, just pretty much like Earth. The largest one is by far the Northern Polar Cap, is much larger than the southern one. Both poles are a mixture of water and carbon dioxide ice. But in the summer for each hemisphere, the carbon dioxide ice sublimes or evaporates straight into gas and goes into the atmosphere. And then come wintertime, it gets frozen back in. But the water ice is the base. It stays there all year round. The North, I've written here, the North Polar Cap, its size, 1,000 kilometers across. So that's a decent size. That is the length of the North Island of New Zealand. So the full length, Cape Reinga to Wellington, that is how big that northern polar ice cap is. Radar suggests it's about 2 kilometers deep, which that's a reasonable amount of depth. So there's quite a lot of water ice locked up in ice, but exposed to the surface at the North Pole of Mars. And the South Pole, as mentioned, it's a lot smaller. It's only about 420 kilometers across, but it's a lot deeper, 3.7 kilometers deep. And once again, that's been analyzed from radar, the orbiters. Now, the third place is around in particular, around the polar caps, in particular around the northern polar caps, there's some very large craters up there, and they have ice in them that's exposed to the atmosphere. The largest one called Korolev, and it's actually so large, it's actually a decent size. If you have a look at, if you haven't got it already, because I'm sure you've all got one of these at home, some of these larger craters like Korolev are actually large enough to actually fit on one of these globes. That's 82 kilometers across, so that's certainly a decent size of permanent ice. So how about, is there any water ice underneath the surface, subsurface? Yet the answer is yes, there is, down to 39 degrees latitude. So let's have a look at that. So you're talking 39 degrees. So here's your 90 degrees at the pole. Here's the equatorial latitudes. So you're talking about here somewhere. So a fair way down the globe, right down there, there's evidence of subsurface water ice. So down to latitudes of 68 degrees, that was discovered by NASA's Phoenix lander here in 2008. And the lander, when it landed, there was no signs of any ice, surface ice, but it's got a little robotic digger arm here. And it started digging into the soil. And lo and behold, just a few centimeters below the soil, they exposed some water ice. And that ice, now that had been exposed to the surface, just slowly sublimed over about 4 days. So that was the first evidence of subsurface water ice. Then in 2017, you're talking further down to about 55 to 58 degrees latitude, coming down further. They found 100-meter thick ice sheets under about 1 to 2 meters of soil. How did they see it? It was a fresh cliff edge that had eroded away and exposed the side of the cliff. And you can see that here. They've colorized it and they've put the ice sheets in blue. So that's 100 meters thick, only 1 to 2 meters underneath the surface. They analyzed that and they estimated from that if they seen that at this latitude, the estimations were probably a third of Mars just underneath the surface has water ice. So about a third of the planet. 2029, that's when they got right down to latitudes 39 degrees. They found numerous sheets of large subsurface ice deposits exposed in the sides of some young, relatively young, fresh craters. Here's the side of the crater. And once again, they colorized it in blue that you could see there. So lots and lots of sheets and deposits of water ice. So you're getting down to latitudes 39 degrees. So just remember, to give you an idea, for example, New Zealand is 36 degrees south. So you put that, this of course was the Northern Hemisphere where they saw this. So it gives you an idea, you know, you're getting down there. So yeah, and the other area that was interest in terms of where the water is today is those 4 subglacial lakes, so lakes underneath glacier, just underneath the South Polar Cap. So here's your southern solar cap, and radar detected underneath all this general region here 4 lakes with water, the largest being length of about 20 kilometers, and they suggest it's probably estimate about 1.5 kilometers underneath the polar caps. You might say, well, how could the water be liquid? It's pretty cold up there, isn't it? And 2 things. One is there's a lot of calcium and magnesium perchlorate. They are salts that are relatively sort of abundant in the Martian soil. And salts in water create brine and has an antifreeze effect, whereby it lowers the freezing temperature down below 0, because everything at 0 degrees Celsius, of course, is the freezing point and water just freezes out. But if you put brine with it, or essentially antifreeze, it lowers that and you're more likely to get liquid water at temperatures below 0 degrees Celsius. Furthermore, they think most likely that the water is sitting in some caverns down there, some chambers with molten lava have sort of still quite warm, and they've got nice little chambers that developed in there, and the water's probably getting some warmth and from heat from those as well. So they're the most common, well, the most 2 factors they said that's most likely keeping that water fluid. So in conclusion, where is the current water status on Mars? There's abundant water ice above the surface at the poles, you know, sort of, you're talking 2 kilometers thick by 1,000 kilometers at the north, and the southern is, 3.7 kilometers deep. There's subsurface water ice up to a third of the planet's got it hidden underneath its soil, and there's 4 subglacial brine lakes underneath the South Polar Cap. So that's where the evidence is today, where the water is. And the relevance of that, of course, is for future astrobiologists, but future inhabitants going to Mars. They're going to want to know where the water is. They want to base themselves where the water is. 2 reasons. One is to live off, you know, to drink, to cook with, to wash with, and so on. But the other one is to use for fuel. They separate into oxygen, hydrogen, and use it as fuel for their rockets. So it is crucial that they want to know where the water is. So let's look at some prominent, relevant geological features. So here is a topographical map of Mars, whereby your red colors, red hues are high altitudes, and it goes down through orange, yellow, green, down to the lower latitudes of blue. There's a few things here to point out. One is that you can divide Mars sort of quite readily into 3 main regions. The two in particular, the top one and the bottom. The bottom, the southern hemisphere here, they call it the southern highlands. The crust is a lot thicker. It's called the crustal dichotomy, where Mars's crust is a lot thicker. It's about 38 kilometers deep on the lower half, the southern hemisphere, and the upper northern hemisphere, it's only 32 kilometers deep. So you've got 6 kilometers depth difference, and they call that the crustal dichotomy. How did it come about? No one really knows. The general consensus, probably early on in the formation of Mars, some sort of collision on one of the hemispheres created that effect. So you've got the southern, what they call the highlands. They are heavily cratered, which tells you that that's an older surface because there's been no other geological forces. And they dated at about 3.7 to 4.1 billion years old. And you might say, how do they know that? They do it by what they call crater counting. It's a method you're able to age surfaces with. An older surface has got more craters, more variation sizes, more densely packed craters, and larger craters. A real young surface, of course, should have no craters, but as the surfaces get older, you start seeing more and more craters. And you might say, well, why the different sized craters? Gives you an idea in different ages and stuff. Because early on in the solar system, when it was just first formed, the outer gas giants migrated and shifted around a little bit. And that disturbed a lot of asteroids and small rocky bodies, which headed into the inner planets and slammed into the inner planets. These created loads and loads of large craters. They call it the late heavy bombardment period. So if you see a lot of huge craters, you know it was obviously during that period. And they think that period was probably about 4 billion years ago when that happened. So now you might say then, well, how do they correlate an age with the numbers and size of craters? Apollo moon landings. When the astronauts went to the moon, they brought back moon rocks, which on Earth they used their radioactive dating method and could tell the age of the rocks. They then correlated that with the crater counts and the types and natures of craters that were in that region of the moon, and they were able to correlate it from there, and it seems to work quite well. So that's called crater counting to date surfaces. So you've got the southern highlands, the oldest, high up, lots of craters. The other extreme, you've got the northern lowlands, and that's mainly a flat lava flow, very low, very flat, very few craters, and that's no older than about 2.8 billion years. We're going to talk, that's very relevant because we're going to talk about that later, because that's the site of the proposed Martian ocean in the past. Then there's the central area here, called the Hesperian region. And that's very rich in volcanic activities. And you can see, for example, this Tharsis bulge here. This is a giant volcanic plateau. This area takes up about 25% of the Martian surface. It's full of volcanoes. You've got 3 main big volcanoes here. Off to the side, you've got Olympus Mons. That's the largest volcano in the solar system at about 22 kilometers high. It's 3 times the height of Everest. Why can volcanoes get so high on Mars? 2 reasons. One is smaller, so it's less gravity. So it's gravity that pulls things down as they try and get higher. So it's allowed to get higher and higher before rocks start to fall down. And the fact that Mars does not have tectonic plates, thin tectonic plates like Earth that slide around over the top of one another. It's what they call a single plate planet, one big thick plate. So that big thick tectonic plate is able to support heavier structures before they sink down. So volcanoes can get very large. Then there's this region here called the Arabia Terra, and there's loads and loads of depressions here. And up till recently, they thought they were probably just craters. But recent observations and spectroscopy have shown that they're full of actually volcanic ash, whereby this whole region almost certainly was just full of super volcanoes going off. And they call them calderas, as the name given to when you get a big depression in the surface from volcanic activity. So this whole region here was just full of volcanic activity. Now, that is also very relevant to what we're going to be talking on later on, hence the purpose of this slide. And the surface here is somewhere between the two. It's somewhere between 3.7 and 2.8 billion years old. So that tells you roughly when the volcanic activity was going on as well. turn off their mute. I've done that. That's good. Okay. Now, the evidence for past liquid water. Let's move on. And there's two main lines of evidence. Geomorphic, in other words, sort of gross, sort of big geological features that you can see. And these are predominantly from observations from orbit. And spectroscopic examinations of various rocks and minerals, observations from the ground, from the rovers and so on. So let's first of all concentrate on the geomorphic features. And there's four main things we're going to look at here: valley networks, outflow channels, lakes and deltas, and the Mars hypothesis, the Mars ocean hypothesis. So yeah, valley networks are essentially, particularly if you go up into the southern highlands, these are very, very prominent up there. It's essentially large systems of just multiple channels, all branching off one another, like branches off a tree, just branching. Their width is usually anything up to about 10 kilometers wide. Length, they're usually hundreds, sort of 200, 300, 400 kilometers long. And very clearly, where some sort of liquid, which they assume is liquid water, has clearly flowed down through here, you can see all the branches coming off. And they flow down from the Southern Highlands. The fact that they're in the Southern Highlands, remember that's the older surface, so that tells you straight away whatever caused these valley networks was more than 3.7 billion years ago. To a lesser extent, they do come down into the central regions, and then they stop after that. So that tells you that that process was predominantly before 3.7 billion years ago, that there was a little bit of it going on up to about 2.8 billion years ago, and then that process just stopped after that. So you can now starting to see the logic and just getting your head around some of the main geological features, the different regions, and how to age a surface and the relevance for aging a surface. It gives you insight into what processes have occurred and when they occurred in the history of a planet. So these valley networks, you think to yourself, well, what sort of climate scenarios could there have been that would have been responsible for these? And there's very good arguments for all four of these scenarios. Was the climate warm and wet? In other words, it was rainfall, rain coming down and surface runoff and erosion of the rocks. Was it a warm but dry environment? In other words, no rain, but it was warm, where geothermal water comes up, spring water will come up, rise up over the surface, and then go flowing down the surface. That's viable. Or was it cold and wet? In other words, it was cold but wet. It was that instead of rainfall, it was snow coming down, and then glaciers forming. And of course, glaciers move downhill and they quite happily erode into surfaces. Or was it cold and dry? In other words, just ice sheets and glaciers, but there was water, channels of water that had melted underneath those glaciers and ice, and that they were moving along underneath the ice, but above the ground, sort of eroding, causing those valley networks. So there's good arguments for all four, but as research went on, by far these days, the most favored one is warm and wet climate. The reason being is as they put more orbiters up there with more high definition, higher resolution cameras in that, they could see the branching effect of these valley networks were high ordered. In other words, just not one going down and branching off to two or so, but they kept branching out. There was a lot of terraces down the side of them, bedrock being exposed, and that tends to favor rainfall. Rainfall and surface runoff on Earth is what you typically see causing that degree of branching and terracing. So that's the most favored. So that tells you that you're immediately starting to favor that Mars, probably 4.1 to 3.7 billion years ago, was probably warm and wet. So we've already worked that one out now ourselves tonight, just by knowing the geology, knowing how to date a surface, and then knowing what it's showing us. They also see these, outflow channels. So outflow channels, once again, are very channels. You can see where water's flowed, but instead of being narrow and sort of yay long, where water's just flowed on down, these are really wide, deep, and long. They can go for thousands of kilometers. This is the KC Valley. This is about half of it, what you can see here. A lot of my screen is blotted out by my little pen, what I've written here, but it's about 3.5 kilometers long, the full thing. My next slide actually shows you how long it is, which incidentally is twice the length of New Zealand. New Zealand, I think it's about 3,600 kilometers. Sorry, no, New Zealand's 1,600 kilometers long, and this is 3,500. I don't know whether that says something about the length of the outflow channel or the size of New Zealand, but anyway, I like it in a small country. But so these things are features. Look here, you've got all this that's been streamlining down here. You got these streamlined islands in the middle and the width of it, the width of it all. That indicates that this whole picture, instead of being consistent with a trickle of water, this is consistent with some process that's created a sudden release and gush of high volume, large volumes of water at high rates. It's been dry, then whammo, huge amounts of water have just come from nowhere and just flooded a region. And that's typically that causes that sort of picture on Earth. So something very sudden has gone on there and caused that. It appears that they've come where they originate probably from depressions or irregular craters or irregular patches in the ground, which we're going to have a look at shortly. So that's outflow channels, much wider, longer, deeper. So here's the picture of the full KC Ballast. Here it is here, starting right up, and it goes for 3,500 kilometers all the way. And look at all these huge big islands in the middle where water's been streaming down. And that's typically a sign of a flood. And it goes into Planitia, which is a large plain down there. And you're probably thinking, ooh, water's flooding down there. Water probably pooled down there, in which case you'd be right. So now I mentioned where these things start. And yeah, there's sort of depressions in the ground, or what they call chaotic surface, where it's just all jumbled and mumbled up. Typically where these start. But the general idea is from geologists is most likely you had these reservoir of water that was going on. And the water was just quietly building up underground. And I think I mentioned the previous slide, I can't see it here, but you would have seen it from the previous slide. When did they see all these channels? You're looking at about 3 to 3.3 or so billion years ago when they saw this. So these came after the network valleys when the water was flowing and after it was sort of warm and wet. But so suddenly you've got a scenario where water's starting to pool underneath the ground in these reservoirs. And with the weight of the ground coming down on it, plus some tectonic forces, maybe an asteroid might have smashed into the surface as well and triggered it. But the bottom line is the pressure would build up and up in these underground reservoirs. Something would trigger it where bang, the surface would explode open, and you just get this sudden outburst of large amounts, high pressure surface water that just floods on down to create these outflow channels. So they're called aquifers. These are these big deep reservoirs under high pressure, large volumes of water. And these were obviously in a period after the, or sort of near the tail end of the valley networks, when the valley networks are starting to get less and less frequent. You don't tend to see these in the Southern Highlands. You tend to see these more in that sort of central Hesperian, central equatorial region flowing down towards the northern lowlands is where you find these, which tells you the dates when these occurred. So around about the 3 billion year mark. Now, okay, so that's valley networks and outflow channels. A lot of the large craters, and where do you get the large craters again? Older surfaces, so in the Southern Highlands, you get a lot of large old craters here that have got a lot of features suggesting they were from ancient lakes. And so here's Holden Crater, for example. It's 160 kilometers wide. The evidences suggest that was a big lake. Look at these little channels that are going in. See the little breach in the rim, sort of little breaches in the rims here of the crater where water was probably flowing down and flowing into it. Some could have been flowing out of it. You can see like a little, what they call alluvial fan, or a little delta, sometimes they're called deltas, where you get, that's where you get sediment material coming from a river, flowing into a standing body of water, and the sediment just flows in and spreads out like a fan. You'll often call them alluvial fans, or sometimes you'll hear the word delta, like the Mississippi Delta and so on, where the Mississippi River flows into the Gulf of Mexico. So this, all the base, notice the base is all smooth, so it's sort of sedimentary rock where probably a lot of sediment had settled down there. Where do you see that? The beds of lakes. So there's good evidence to suggest that this was a lake. You know, once again, when are we talking? The surface is 3.7 billion years old minimum. So you know around that sort of 3.7 billion year mark, years ago, Mark, that there were probably lakes going on here. Now, to give you an idea, you might think, oh, yeah, 160 kilometres, that's big, but how big is that? I've tossed in Lake Taupo, New Zealand's largest lake in here. Lake Taupo is about 46 kilometres in length, and look at it here. So I've put that into proportion. You can see the, you fit about sort of more than 3 Lake Taupos end to end in here to fill up Holden Crater. So that gives you, if you look across, you pull into Taupo and you look across the full length of Lake Taupo, that's a big lake. Well, you imagine looking across, sort of 3.5, 4 times that. I think this was on Mars all that time ago. So that's Holden Crater, a lot of craters like that. This is Elvis Crater, also in the Highlands. And notice all the sedimentary around here, but look at all this. This is a massive big delta, 115 square kilometers. So clearly a lot of fluid water was coming in here, carrying sedimentary material with it, moved into a still water or slow moving water in that lake and deposit itself. So that's typically what you see on the dry beds of lakes on Earth. So it's pretty strong evidence. You can see there was liquid water, all right, flowing on Mars, and it was most likely in a warm, wet climate. And most likely, you're talking sort of that 4 to 3 billion year sort of time frame. So it's already starting to form a picture. Then, the proposed Mars ocean hypothesis. And you saw that picture early on with some of those prominent geological features, and you saw that, that most of all the northern hemisphere of Mars is just all lowlands and it's all flat lava. And you think, where do you see these big flat plains? Look at the dry salt lake beds and stuff like that in the US and around the world. It's all flat. And so there's very good evidence that 1/3 of the surface up here in the northern lowlands between 4 and 3.5 billion years ago was just one big ocean. And that would fit with the picture of rain and lakes and that, because particularly if you're going to have precipitate like rain or snow, you need a large volume of water somewhere to complete the hydrological cycle, water to get evaporated, shift around, and then come back down again. So that fits in with that quite nicely. What is some of the supporting evidence for that? As they explore with their orbiter observations here around these borders here, the sort of the proposed shoreline, if you will, of the ocean, there's a lot of sedimentary deltas along here. Valley networks are coming down here that are draining into here, and they all seem to stop. Remember that picture that I showed you of the KC Valley Outflow Channel? Once again, that went into a nice little flat here, the Chryse Planitia region. So all evidence points towards that everything was coming down, water was flowing down into a large body, and the general speculation, and it would fit nicely with the theory, is that most of that northern lowland was all just one big ocean. Now, there's another bit of supporting evidence for that, is the H2O measurements. You might say, oh, what's that about? It's about water. Let me explain. Water as we know it on Earth is sort of a form of light water. It's H2O. So it's 2 hydrogens and an oxygen. And the hydrogens, as you know, the nucleus of the hydrogen is just 1 proton. But hydrogen has an isotope called deuterium. And deuterium has an extra neutron in it. So a deuterium is a proton and a neutron. And that's sort of a heavy hydrogen, if you will. It's an isotope of hydrogen. So heavy water, instead of having 2 normal hydrogens, just for their protons with an oxygen, heavy water has got 1 hydrogen with its proton, but a deuterium, which is an isotope of hydrogen, a proton and a neutron. So they call it heavy water. And we've got heavy water on Earth too, and there's an accepted ratio that they work out that's natural on any planet, the amount of the proportions, if you will, of heavy water versus light water. And when they do measure the water ice on Mars, there's a disproportional amount of heavy water compared with the normal standard light water. And that indicates that a lot of the light water has gone missing and most likely evaporated. It's been lighter, and it makes sense. If you've got heavy water and light water, of anything really, it's the lighter stuff that's going to go first. So that's another indicator that Mars did previously had much larger volumes of water than what we see now in the past on Mars. So that's more supporting evidence that Mars had a lot more water than it's got now, and it's probably evaporated away, that it was probably part of this northern ocean. So that's sort of the geomorphic features, mainly observations from orbiters. We'll now move on to the spectroscopic examination of rocks and minerals, which is predominantly done by the landers and rovers in particular. Once again, my screen is mostly blotted out, but the Subsurface Crater, that's over here, excuse me, because I can't see myself, but I know it's sitting over here somewhere, Subsurface Crater, and that's where the Spirit rover landed. And then we're going to have a look at Meridian Planum, which is over here, and that's where the Opportunity rover landed. And then Gale Crater over here, where the Curiosity lander landed. And then we're going to talk about Martian meteorites. Now, what do you notice about these three landers, by the way, guys, and also this Pathfinder here and Viking 1 site here, is they're all around sort of those equatorial regions, aren't they? Because that's where there's two reasons. One is that's where the money is geologically. Look what you've got going on here. The northern lowlands is just sort of young lava plains. You're not going to get a lot of information there. But look, all around these regions here, you've got a real mixed bags, volcanic areas, areas that have flowed into proposed oceans and lakes and so on. So it makes sense to land here. Why haven't they gone into the highlands? Because it's the highlands. Your crust, remember, is 6 kilometers higher, which means you've got less atmosphere and less relatively denser atmosphere to come down and break with your parachutes. So the atmosphere is too small up there and too thin up there to come for a craft to come down and land properly. They probably will one day, but currently, engineering purposes, it makes a lot of sense to land into some lower region where you've got more atmosphere, more room, and thicker atmosphere to break and land on the surface. That's where you find the lion's share of all your rovers and your landers are all around these equatorial regions, rich in geology and just engineering wise easier to land. Okay, so Subsurface Crater, here it is here. That where Spirit landed, it was chosen for its appearance. Once again, you've seen this picture before with Holden Crater. Doesn't it look like an old ancient lake bed? Look at these channels coming in. There's channel coming in here, channel coming in here. Look, this looks like some sort of alluvial fan or delta going on. This looks like something like that here, where sediment sort of fanned out. Look at the base of it here, nice sediment looking base. So that just looks lovely, like an ancient lake. So it makes sense versus just look at pretty pictures from your orbiters at them like Holden Crater. Hey, get down there an equatorial one and land it and take some samples and have a bit of a sniff around, see what's going on. The size of this crater is slightly bigger than Holden Crater. It's 166 kilometers across. So here's your Lake Taupo at 46 kilometers across. So you can see these are really large lakes that Mars did have once with a lot of water. Here it looks what it would have looked like filled up. So what were some of the results? So when they explored, is that certainly they looked at the soil and the exposed outcrops of rock, and they did analysis of the minerals. And the bottom line is they found a lot of sulfates, goethite, carbonates, minerals that only form in the presence of water. No water, you don't get those minerals. You only get those minerals with the presence of water. So that's instantly telling you there was water there. The rocks lacked olivine. Olivine is a mineral you often see on Earth, and it's formed in dry areas, and it typically decomposes in the presence of water. And hello, there was no olivine there. So that's another clue. Something got rid of the olivine, which is normally ubiquitous in a lot of soil. So there was obviously some water there. They also found some of the soil was quite rich in silica, and that on Earth that usually is associated with geothermal hot springs coming up, with warm water coming up from the ground, spreading out. So once again, that also gave you a hint that water was coming up from the ground as well, and it was wet. So the general conclusion was this was a shallow lake, probably 3.7 to 4 billion years old, which all ties in with the water and those valley networks, that warm, wet climate in this area. Remember, this was they call it the Noachian period, and it was the period when that southern highlands were forming, the valley networks were there, with the climate was warm and wet, and rain was coming down from the water coming from the Northern Ocean. Rain was coming down, forming these valley networks, which led into these lakes where water was forming. Remember, it was after that that the water went underground into these reservoirs and then exploded upwards to create the outflow channels. So isn't that lovely? So Meridiani planum, this is where Opportunity landed. And this is just a cool view of the plains there. It's called Meridiani because if you look at your globe, you get your globe out later because I know all of you have got one secretly at home. It's down the Meridian line at sort of 0 longitude is the nice big plain. So they call it Meridiani planum. So that's it there. So some of the results, they found a lot of these hard spherical balls of minerals called blueberries on the surface. And they're made up of hematite, which you also get them on Earth. And it's an iron oxide mineral. Typically, you get them on Earth in hot water springs or whether you get standing warm water around, like Rotorua and stuff, with springs coming up. And that's where you see these spherical blueberries on Earth. So that was very sort of indicated there was probably hot springs there and as well, and water just standing around. The next interesting feature here in the rocks, these sort of veins of gypsum running through sedimentary rock. And gypsum is a sulfate mineral that, once again, forms in water. And the fact that you had these veins of this gypsum running through the sediment rock, once again, sediment rock, hello, where does that come from? Water deposition. So obviously there was water there. Obviously there was sort of minerals forming in the water, and there was underground flowing water for that to have occurred. So once again, you can see the picture building up here. There's no doubt about it. There was flowing and still water on Mars, and it was certainly conducive for that climate. They found like a lot of the rocks here had these little sort of microscopic little holes. They call them bugs, V-U-G-S, little holes in the rock. And typically what causes these, when you get sulfate minerals dissolved that in the rock, and sulfate once again is a mineral that typically forms with water, and then more water comes along and dissolves them, and it leaves you with these little sort of microscopic little holes or bugs sitting in rocks. So they saw those there. That was an indication. And then some sort of larger features here, rock laminations and crossbedding. So you can see rock laminations going on here, crossbedding at the rock laminations at different levels. You typically see that on Earth where you get gentle flowing water. So there was a lot of evidence at Meridiani planum, once again, of surface liquid water on Mars. So how about Gale Crater? That's where Curiosity landed. So it was chosen because, once again, a huge big crater here, and it had a lot of channels flowing in and out of it and so on. It's also got a big mountain in the middle of it called Mount Sharp that's 5.5 kilometers high. And it appears to have been formed by just sediment laying down over the eons, over millions of years. Sediment layers just built up to multiple layers. So obviously that's going to be a minefield of geology, not only to see what's there, but to see how the environment, the climate changed over millions of years with the different type of sedimentary deposits there. So so Curiosity landed over here. There's a nice big delta here they've explored, and it's worked its way over, and it is now working its way, and it's rising up Mount Sharp. The crater's about 3.5 to 3.8 billion years old. Once again, that fits in beautifully with our story so far of these warm, wet climate in the early stages, pre-3 billion years old. That's with a warm, wet environment, rain, valley networks forming, water flooding into these lakes in the Northern Ocean as well. A lot of sediment being laid down. So you can see the pictures starting to unfold very nicely. So some of the close-up things here, what they saw multiple alluvial related deposits, so yeah, big delta fans and so on. They saw a lot of sedimentary rock, aqueous sedimentary rock in particular, mudstones and sulfates are the two sedimentary rocks typically. A lot of pebbles and gravel. Where do you see that on Earth? Flowing water. And this is all the sort of stuff they were seeing at Gale Crater. So here's quite a cool, this is an artist impression, a model image of Gale Crater in the past. That was presumed about 3.5 to 3.8 billion years old. I've put down here, I can't see it out of my sight, a little bit behind all the zoom panel that's going on here, but I put a not to scale, but I just put a Lake Taupo to remind you. So this here is 154 kilometers across. Lake Taupo was what, 46 kilometers across. So this would be Lake Taupo, the size of this here. So isn't that a beautiful scene? But that's just a lovely, beautiful, tranquil scene. Take it in, guys. That's what like a Gale Crater probably looked like, say 3.5 to 3.8 billion years ago. Beautiful. Have a drink of water while you're taking it on board. Okay, yeah, Martian meteorites. So meteorites, as you know, come from the solar system and smash into Earth, and we have a look at them. And you might say, well, how do they know they came from Mars? Well, meteorites have little bubbles in them and full of air. And when they analyze the composition of the air inside the rock bubbles, it matches perfectly with the composition of the atmospheric air on Mars, as measured by the rovers. Even the 1970s Viking landers were quite capable of measuring the composition of the air on Mars, and it matches perfectly. So that tells you that meteorite is from Mars. You can get them from the moon as well. They come to Earth quite happily. And the mechanism behind it is a large asteroid will come down, smack into the surface of, say, Mars, rocks fly up, get expelled up high at a high velocity, escape from Mars, and they just sort of head into the inner solar system. After a few million years, they work or a few billion years even, they work their way around into Earth's orbit and path and come through our atmosphere, and they analyze them. And when they were able to analyze them and look at the various minerals in these meteorites from Mars directly, with the high sophisticated, more sophisticated spectroscopies in the laboratory, they found they had a lot of minerals and so on in these meteorites that formed with liquid water. So once again, that's further evidence that's come. We're not having to worry about sort of spectrographs and stuff on Mars. We can put them through the through the big powerful ones on the labs on Earth as well. So that's looked at the big features from the orbiters, the valley networks, the outflow channels, the signs of previous lakes. We've the ocean hypothesis, a lot of evidence for. We've now looked at what they've seen at Subsurface Crater, Meridian, Plani, Gale Crater, and the meteorites. Let's have a talk about the early atmosphere and climate history of Mars. Was Mars cold and dry once when it was young, or was it warm and wet like we seem to be getting some evidence for? And what if the atmosphere and water, because obviously now there's very little atmosphere there now, and no water, it's liquid water that we can see. So what would have happened to the atmosphere and the water perhaps? So an argument for a cold and dry young planet is Mars supporting that. Mars is 50% further out from the sun. You saw in Josh's news how you had the sun here and Earth's orbit here, and Mars was about 50% of the way out. And that equates to about 43% of the energy of what's called solar flux, or the energy from the sun that we get on Earth. Mars only gets 43% of that amount, so it gets a lot less sun energy. Plus 3 just because of stellar evolution on the main sequence. The sun 3 or 4 billion years ago, which is what we're interested in now, the sun would have been 25% luminous or powerful than it is now. So it's not easy, it's not hard to imagine Mars being a much colder and drier place. Now it says periods of high obliquity. What does obliquity mean? Obliquity is just a fancy word to describe the axial tilt of the planet. Earth has got an axial tilt of 23.5 degrees. It gives us our seasons, and it's relatively stable. It doesn't alter around a lot. Why? It's because our moon. We're lucky. We have a moon that, relative to the size of the Earth, it's relatively a decent size mass in comparison to the size of the Earth. So it tends to keep the Earth's axial tilt reasonably stable. Mars doesn't have that luxury. It's just got a couple of probably captured asteroids, a couple of tiny moons. And because of that, it doesn't get that stability effect that a large moon like our moon gives our planet. So the obliquity or the axial tilt becomes unstable. It moves around to a lot of different extremes and so on. So there is a lot of evidence that Mars has experienced degrees of high axial tilts, and the effect that has, it tends to, if your planet's more stable like that, like on Earth, you tend to be reasonably stable. You have a nice cool, both polar caps are relatively cool, and you get warmer around the equator. You tilt something up on its side, and a lot of that cold and snow and the glaciers gets redistributed further down towards the equatorial latitudes on a planet, those low latitudes. So once again, that would add argument that there was obviously a lot of global snow and glaciers down to lower latitudes with Mars. And that would have allowed, whereby you had a lot of the surface was just covered with a lot of ice sheets and glaciers with flowing and standing water underneath those glaciers moving along. So you had your lakes, you had your little channels and so on, but it was all moving around and causing erosion underneath these sheets of ice and glaciers as opposed to on top. But the problem with that is it doesn't explain the complex branching, high degree of branching that they see with these valley networks, along with the terracing down the side of the valley networks, the bedrock erosion that you see. That really, really does favor something that precipitate like rain or snow coming down onto the surface. So that points you more towards it was a warm and wet planet. And so the argument, so looking for an argument for a warm and wet young planet, young Mars, the problem with that is you would have needed a warmer and thicker atmosphere than you've got to have created that warm, wet young planet. So where does that come from? Well, the solution to that is the argument is threefold. One is volcanic activity releases a lot of carbon dioxide and water vapor into the atmosphere. And you know, both those are very strong greenhouse effect, which retain the heat in an atmosphere. And this is one of the other points that I showed you, that slide right up front of some of the geological features on Mars. You saw yourself that central region, that fastest bulge that takes up 25% of the surface of Mars, just one giant volcanic plateau. The three big volcanoes lined up, Olympus Mons next to those, the largest volcano in the solar system. Then you saw that Arabia Terra region, that large area of this huge big volcanic calderas that obviously just spewed out huge amounts of volcanic ash and gases. So we know the evidence is there that Mars was really, a lot of volcanic activity was going on in its past. Secondly, a lot of methane will often accumulate underneath glaciers. And sometimes if those glaciers then melt a little bit, the methane is then released. And methane is the king of potent gases that aggravate and cause the greenhouse effect. And then, asteroids and comets were probably early days of Mars as well, when the solar system was chaotic. So remember, you saw all those large craters, evidence that Mars just got thrashed, it just got hammered in the early stages of the solar system. Large asteroids and comets just ramming into it. They themselves generate a lot of heat, and computer models certainly support that the number of impacts by analyzing the craters would more than explain to create a nice warm atmosphere. So there's plenty of evidence to suggest that the atmosphere was quite warmer and thicker than it was in today. So just talking about some more problems from there. So if that was so, what happened to the atmosphere? What happened to the water? And so on. And how did the atmosphere change? Why did it change? When did it change? So let's have a look. So possible solutions. The carbon dioxide can get incorporated into rocks as carbonates, but the orbiters are pretty good, and they sort of doing spectroscopic examination of the rocks below them. And there's really no substantial quantities for carbonates in the rocks of Mars, certainly not to account for the CO2 that would have had to have been in the atmosphere before. Condensation of CO2 might have occurred at the ice at the poles, but we know the polar caps are mostly water ice. There's not a lot of carbon dioxide ice up there. And besides, summertime, it sublimes into the atmosphere anyway in spring and summertime. The other thing is there's a dedicated atmospheric research orbiter, satellites on Mars, one of NASA's orbiters called MAVEN, and it certainly confirms that this process at Mars, this atmosphere has been lost to space as we talk. How much? It's about two kilograms of atmospheric molecules per second to this day is still being lost from Mars to outer space. You might think, whoa, why is all this happening? And let's talk a little bit about that. Now, on Earth, we are very lucky. We're a reasonably sized planet, so our inner core, made of iron, is still molten. And as the Earth rotates around, the molten iron sloshes around. Iron conducts electricity, of course, and what happens when you get a moving electrical conduction and so on, you get magnetic fields get created. So we have, because of our sloshing iron, we have this protective magnetic field. It's called a magnetosphere, or a global magnetic fields around us. And the importance of that for us is that all these high energy charged particles in part of the solar wind process go charging out from the sun, rip into the planets, into the atmosphere, and quite happily will erode away an atmosphere. But if an atmosphere is protected with a magnetosphere, such as what Earth has got, the charged particles instead go zip down the magnetic field lines down towards the poles of the planets, and they lose their energy. And it's those that cause, of course, the lights, the Australis, Australis Borealis, and so on, the northern and southern lights, Borealis, Australis, and so on. So, so that's what protects us. Now, Mars is a smaller planet. It's only, the diameter of Mars is only half the diameter of Earth, so it's a lot smaller. So it follows its surface area is a lot larger in comparison relative to its mass size. So for that reason, it cooled off a lot quicker. So when it cooled off, the liquid iron core solidified. And from there, Mars lost its global magnetosphere, that nice protective magnetic field around it. And without a magnetosphere, yep, the solar wind charged particles came in and just constantly erodes the atmosphere. Yeah, and there's that figure there, 2 kilograms per second to this, at this current day is still being lost to space because of the solar wind just eroding, racing into it. So let's start summing up our 4 main points here and the likely sequence of events, and then some sort of conclusion about what happened to Mars. So what do we mean? The geomorphic features of past surface and subsurface of water, liquid water. You've got those valley networks up in the southern highlands from rainfall, probably sort of 4.1 billion years ago. Then sort of 3 to 3.3 billion years ago, somehow a lot of this water appeared to go underground. You get these sudden releases of large volumes of underground water, which caused these outflow channels, which then flooded down towards the Northern Ocean. You could see these lakes and deltas and the large craters of the highlands, which were probably 3.5 to 4.1 billion years ago. And as mentioned, the possible large Northern Sea, they estimate that was probably about that same sort of period, about 3.5 to 4 billion years ago. Just going to flip through there. So I thought I missed a slide. The rock morphology from the minerals, the cross laminations, and so on, the layering of rocks, the things like various minerals like gypsum minerals that's embedded in sediment rock and so on, that points strongly towards wet conditions. Once again, probably 3 to 4.1 billion years ago. The third thing was, we know that Mars was highly volcanic in its days. It had a lot of large impacts because we see the big volcano sitting there. We see the multiple masses of large craters. So we know they're capable of providing a thicker, warmer atmosphere. So we know that those activities were pretty prevalent at the time. We know that Mars has gone through a cooling and going through loss of global magnetosphere and atmosphere, and that's the prime mechanism for the loss of the atmospheric carbon dioxide and oxygen that would naturally go with it. So the likely sequences of events, the early carbon dioxide and water in the early days, the atmosphere would have been rich in water vapor and atmospheric carbon dioxide. It was provided by extensive volcanism that would have raised the atmospheric pressure and the temperature in the first 500 million years. Then you had a lot of impacts after that would have released a lot of methane trapped underneath the ice at the same time, and just released energy from those impacts. Then you had sort of between about sort of 3.8 and then petered off about 3 down to about 2.8 billion years ago. You had a lot of rainfall and snow, flowing ice, valley networks formed. You had this water flow from the highlands down to form these lakes in these northern ocean, probably about 3.5 to 4 billion years ago. The evidence suggests the loss of the magnetosphere started. It's a long story, it's a story on its own, but the evidence points towards that process probably started happening about 4 to 4.1 billion years ago, where the magnetosphere just got weaker and weaker. So that heralded the onset of continuous erosion of the atmosphere, which took about 1 billion years to take, to get a real grip on it, whereby the atmospheric pressure and temperature started significantly getting lower and lower and lower. And it makes sense that liquid water at that stage would have turned to ice and to glaciers, and then would have also buried underground. And that would explain the period of time that you see these outflow channels. The water obviously was starting to head underground. And that was the next slide. So then you had the release of this high pressure groundwater to cause these outflow channels and massive floods. And from the surface, in the crater counts, we know that was about 3 to 3.3 billion years ago. And then eventually just the surface atmospheric pressure and temperature just dropped lower and lower and lower. Any surface water then just what was left just evaporated and was lost to space, and the remaining groundwater freezes into that subsurface ice that we can see today, that we can uncover. So what can we conclude? Mars was once warm and wet with surface liquid water, when probably 4.1 to 3.7 billion years ago. Mars experienced after that sort of mixed regional conditions, including snow, ice, and glaciers. And then about the last 2.8 billion years ago, Mars has been just cold and dry, and just with the inability to support liquid water on its surface. So just here's a little bit of food for thought. So that's the general conclusion that we can make from the evidence. As you see, the evidence is very strong. Food for thought. Life arose on Earth, these sort of estimations, probably about 3.7 billion years ago. 3.7 billion years ago, conditions on Mars were far more favorable and suitable for life to get started than they were on Earth. Earth was still a pretty hostile place, and it sort of raised a few eyebrows. How did life get started here 3 billion years ago? They had a far better chance at that stage getting started on Mars. We know that meteorites can travel from planet to planet, from Mars to Earth. We pick them up and examine them, see they're from Mars. We also know that a lot of meteorites and rocks and stuff and asteroids and so on and comets have organic molecules on them, the sort of the building blocks of life. So possibly, are we all Martians? Did life come on Earth come from Mars? Are we all Martians? Sometimes when I look at the news, what's going on every day, I think to myself, that would explain a hell of a lot, actually, what's going on around here. But anyway, so that's food for the thought for the night. We all could be Martians. So what are you going to do once your homework? Just tomorrow or later tonight, just bring up on the internet, bring up some lovely, enjoy some lovely images like this. It's cold, it's barren, but it's beautiful. So bring out some images like this, just enjoy them, but then reflect on its past and look at the picture, look at a bit deep past the cold and the barren look, and look at those little rocks and stuff, how smooth they are, and think about the different soils and minerals that could be in there. They're all pointing towards liquid water once flowed over these surfaces. And then reflect on its past, how the climate would have been, and go and tell someone about it if you want. So yeah, that's what you can do from here. So thank you. I hope you've all enjoyed Liquid Water on Mars, a story of climate and change. So I'm ready to take any questions. I'll rely on you, James, if there are any questions in the chat room.
It is an awesome picture, Chris.
My cat, Stella, has actually been on my side. I was so tempted to pick her up and put her up here, actually, but I refrained. She's hungry, so she's not not fed. She's already had about 3 meals today. I don't know where she gets it from. But anyway, yeah, so yeah, that's my Martian cat. So any questions there in the chat room, James?
Nathaniel, I think he's got a question. So if you want to unmute there, Nathaniel, unmute yourself. You can pop your video on if you want or not.
No, I'll just keep unmuted. Are there any different properties of water with deuterium instead of hydrogen?
Yeah, okay, so yeah, the heavy water versus the standard light water. It's either heavy or light. You're probably saying, hey, is because light water is H2O, standard hydrogen, proton, and the oxygen. That's your standard light. And I've introduced the idea that there's heavy water, which is a deuterium, which is the isotope, proton neutron, and a standard hydrogen, just a neutron with the water, are used. So there's only one other combination. I presume that's what you're alluding to, is the deuterium with oxygen.
Yeah.
Not that I'm aware of. I may be corrected on that. You may want to just look that up, just Google types of heavy water, but that's the only other combination. And I know they do the testing, like for example on Mars and stuff, and that's with spectroscopy. It's predominantly for the hydrogen deuterium, the HDO. Now, whether there is some D2O, just look. I don't know. Damn good question though. Just Google that one if you like, and just have a look. But if there is it wouldn't be much, because predominantly with heavy water, it's usually deuterium and hydrogen with oxygen.
Okay. And would they like have any different chemical properties, or are they just functionally the same?
Yes, good, a very good question. I think functionally it's pretty much the same. There is some subtleties with how it behaves, interacts with some stuff. And the reason I know that is because if you look at the Sudbury experiment for solar neutrinos, they use hard water for that. They use HDO for that. So if you look up the search for solar neutrinos, the Sudbury, SUDBURY, it's in a copper mine deep down, a few kilometers down in Canada, and where they won they won the Nobel Prize for it. Very clever experiment, and that was to do with interactions with high-speed particles and the weak nuclear force. So there's some subtle ones, but I think as far as it's predominantly very similar in terms of reactions. But of course, there's far more standard water around, and that's why we use it.
Thanks.
Yep, good question, Nathaniel.
If anyone else has got a question, just unmute your mic and ask away.
No more. Why don't I show, if I've got no more questions, why don't I show off some of my outtakes? I always have a few slides that I have in there, then I decide not really part of the flow, but they're cool slides and you cringe when you take them out. So I have them as case questions come up on them, but I'll show you some, just one or two of my outtake slides. Outtakes. Okay, so yeah, remember this was the slide, that grainy picture that I opened up with, taken 50 years ago from Mariner 9 of that complex. And someone asked me a question once. They said, look, we've got some more updated pictures of what we were looking at from Mariner 9. I mean, yeah, absolutely. So it's called the Nergal Vallis. And so this is a more modern high definition picture. Isn't this cool? Here's a big lake here. And look at this river, 610 kilometers long, just meandering over the surface of Mars. How cool is that? So that's what we were looking at when we're looking at that, because that was one of the first things when I looked at that image. I thought, oh, what does that look like these days? So that's what that's what it looks like in better definition. One of the other ones that I took out, you probably saw one of my pictures there. You had the Tharsis bulge here, the big plateau, and then from flowing down, you had the KC outflow channel down towards the Chryse Planitia, that big lowland area, and there was that big scar across the sky, across the surface of Mars. That's called the Vallis Marinus, and the Marinus name, of course, as a nod to the Mariner space orbiter, that's that first one. And that's essentially a huge, deep Grand Canyon complex. It's about 4,000 kilometers long. It's the width of the United States from LA to New York. So it just dwarfs the Grand Canyon on Earth. And I forget the figures, but it's multiple, it's about 4,000 kilometers across, wide. I think it's sort of, you're talking 100 or so kilometers wide. I don't know if I put some details on it here, I don't know. But I put I found this picture, a picture of the United States over it. It is huge. And you might say, how on earth did that form? Tectonic activity of the volcanic activity. The Tharsis bulge rose, and it was the powerful forces, volcanic forces coming up, lifting that volcanic plateau, and it just split the crust. And that's most likely, the general consensus is what formed that. So I thought that was quite cool to see that, this size. Mars is not a big planet. As I said, the diameter is only half the size of Earth, but you've got these huge features that just dominate its surface. So yeah, that's just a little bit of trivia.
So Chris, another question, sorry, getting back to like Gale Crater.
Yep.
How do they determine how old those craters are? So in other words, what are old craters and what are new craters?
Yeah, okay. So yes, good question. First of all, you look around the general region. So don't just look at the crater and they go, oh, that crater. They look at the crater in the context of the whole region. And they go, okay, we know that big, sort of 1,000 by 1,000 kilometer region, they do a crater count. They look at the density of the craters, the numbers of the craters and the size of the craters. They then correlate that, which they're very good at doing, with the standard age from the moon rocks that they radioactive dated, and then correlated with the crater, examining, analyzing the size and the numbers and the density of the craters on the moon, and it seems to match up quite nicely. So they look at the general region, and then they look at the crater itself. Do you see craters imprinted on that crater? Like it was an older crater would have craters superimposed on it that have come in, onto its surface or started, slammed into a rim or something like that. So if you see a pristine crater, beautiful rims, there's nothing has touched it, that's a fresher crater than one that's all started to deteriorate. You can see what other craters are superimposed on it, and so on and so on. So it is a whole science in its own field. But yeah, the crater count, the analysis of the types and numbers of craters around it, and then you have a little bit of a look at the crater itself, and you get the gist of how old it is.
Any other questions out there, or have you got more slides there?
No, I think I've just got. Yeah. Forgot. Hey, these are that Arabia Terra, that just that huge big sort of mass cratered sort of looking area full of holes. Just here we are. I've got it over here. This area here. So okay, this is back. This is interesting. How do I manage this? So this is back the front. So here's your Tharras bulge here. There's your volcanoes. There's your Olympus Mons. Here's the Arabia Terra. This whole region, they thought they were craters. But look, here's an image from one of the orbiters from the Mars reconnaissance orbiter. Look how deep and huge these big depressions are. Initially, they thought they were just big impact craters. But so they've done spectroscopic analysis. This is just a papers in the last 12 months or so. And it suggested that it's actually all altered volcanic ash. So these were huge, big openings to volcanoes in the surface. This whole region here was just super volcanoes, just spewing out with volcanic activity. So that's that one there. And I think, that was me just playing around. That's Spirit and Opportunity, what that looks like there. And that's Curiosity taking a selfie of itself. That's an orbiter. And that was me just playing around there, getting a nice sort of, it seems there's a nice panoramic view of Mars, which there is, but of course it's too thin and narrow to put in the slide somewhere. I think that's about it actually. So the calderas, that's the Valles Marineris, the size of the United States. And that's the Nergal Valles, from the grainy picture. Yeah, so otherwise, we're all good there. If anyone's got any other questions, we're good.
I was just wondering, they've detected Mars quakes.
Oh, yes, with InSight, the lander InSight.
So what would actually cause that, considering it's now pretty stable rock for all intents and purposes?
I'm glad you asked that question, James. That's what any politician would say, isn't it, when they don't know the answer? That's an interesting question. I'm glad you asked that question. I think they're still working that out. Good question. What causes it? They're only weak signals, of course, to the point of even the machine itself can pick up aberrations and stuff and false positives and stuff. So they really have to analyze them to see whether they're genuine or not. And no soil, like wind, can on the surface of the instrument. So only you're talking subtle ones that are going on there. And it does. They can't say, oh, that's such and such. And the suggestion is that maybe there is some little bit of not tectonic activity like we got on Earth, tectonic plates. There's no tectonic plates, but the word tectonic meaning crust and movement, a bit of heat going on, even though the planet is cooled down a lot. And the liquid iron core is mostly concilified. I can't get my tongue around that one. It's solidified. That's what I was trying to say. Solidified. And they don't know to what degree, of course, but just enough to stop the magnetosphere, having a decent magnetosphere. Incidentally, Mars does have some little localized, global. localized regions of magnetic activity where they could put a little protected little habitats in. So it just has a little localized one as opposed to the big global one. So it has got some warmth and stuff going on there that I don't fully understand. And remember those subglacial lakes underneath the South Polar Cap? Part of the reasoning behind that they're still lakes, not only as the brine, is that there's probably some little magma chambers there. So there is some warmth going on with a little bit of tectonic activity. In other words, a little bit of lava probably moving around in there. Not enough to, there's no tectonic plates, not enough to cause any current volcanic activity, but just subtle amounts, a little bit of warmth, a little bit of movements going on, a little bit of flexing of some rocks and stuff deep down. And that's most likely what's causing those slight Mars quakes that they pick up.
I was just thinking, if you've got something sort of solid, and this side's facing the sun and it's heating up, this side's cooling, that you're getting expansion here and contraction here. Maybe that's also just causing like,
yeah, interesting thought. Mars rotates very similar. A day on Mars Mars rotates a little bit slower than Earth. The day on Mars is 24 hours 40 minutes, 42 minutes or something. So it's not too bad. It just gets, but it's got the atmosphere to distribute the heat, but you might have a little bit of that going on, but it's not like, say, Mercury.
I was thinking more of like summer, winter.
Oh, okay. Yep, possibly. I don't know. Good question. Yeah.
I suppose just having a look at that photo there, I suppose there's probably rock falls as well.
Yes. Because there's wind.
Lava tubes,
and that's where they have to analyze that data before they come out and go, oh, that was a Mars quake. There's a lot of wind stuff going on, and some dust or something, that's dust that's flying around that flies onto the sensor. And I know those early days with InSight, they found a lot of their signals was actually just was aberrations caused by wind and weather and stuff like that. Because there's wind, and you are going to get a little bit of a rock or something that gets disturbed. Perhaps not that the wind is very strong because the low atmospheric pressure, but it's certainly enough to just throw around a bit of soil and stuff like that. You might get a sort of a rock on a precarious situation. Tumbles, possibly. Who knows? Yep.
Ron just posted something interesting in the channel. I don't know, Ron, can you speak? No. So he was just saying that they've recorded a 4.3 magnitude Mars quake a couple of weeks ago, which is by far the largest that we've seen before, and it's thought to have originated from the old volcanic area.
Right. Yes. Yep. There you go. So once again, indicating the old volcanic area, there's still probably a little bit of warmth and tectonic sort of movements around in there. So the planet's not complete, it's not dead. It's cooled down enough whereby it's lost its magnetosphere, but it's not dead.
Has anyone else got any questions? Either pop in the chat or just unmute yourself and fire away.
Otherwise we'll call it a night.
So Chris, do you ever think we'll see a cat on Mars?
Absolutely. It's on Mars. Yep.
It always amazed me with in Star Trek, with Data, his pet was a cat. Not a dog, a cat.
Yep, absolutely. Yep. All right, I think we're all done.
So if there are no more questions there,
good night, everybody. Yep, stay safe.
Hi there, Joe. Popped up and just said hello. And
thanks, Chris.
Yes.
Thanks everyone for joining us. It was really fascinating, as I knew it would be. So our next talk will be in 2 weeks' time. Just keep a look in the Facebook page and your email for all the details on that. As usual, just keep checking the Facebook page. I'm posting all the interesting news articles every day. And I don't know why, but just the last couple of days, there's been some really, really interesting ones out there on all sorts of topics. New discoveries made, and plans of going back to the moon, and plans of going to Mars. It's just incredible what's happening in this day and age. the news feed just gets longer and longer. Ah, there we go.
Here's
Oh,
Stella,
God, the
everyone.
alien.
Here's Stella. Her name is Stella for obvious reasons. Hey, Stella, you like your food, don't you? She's going to go to Mars as long as they've got plenty of fancy feast up there.
So on that happy note, unless there's anyone else who wants to say anything, I think we'll call it a night.
Right. Good night.
Good night. Good night.
Thank
Thank
you.
you. Thanks all.
Bye.
Nice stuff.
Chris, I have
Yeah.
a question for you.
Yeah.
Well, it's more, I want to ask for your opinion on something.
Oh, yep.
So I have my course selections for the year, for next year.
Yes.
I was curious on your opinion on if you think I should take either Chinese or mechatronics.
Mechatronics?
Yes, so it's a mixture of sort of coding and like physically making something.
Okay,
like-
I would have thought that sounds more sort of scientific and mathematical and scientific.
Yeah, because both have got very good uses, like considering all the stuff that China is working on when it comes to space and whatnot, and being able to talk with them in Chinese would be terrible, but like
But is the language, you probably still, from my experience, when you learn a language like that, just unless you're going to take it to some really big, to a much greater degree for a career, you still stumble on the lingo. And I think if you're focusing on technical side of things, you'd be surprised how widespread English is, and a lot of the technical things in the world are in science communities, all English anyway. But that's why you hire someone else. You get an interpreter. When I say hire, you get an interpreter to do that. None of us, we all need leverage in life. None of us have got all the world's skills. I'd be inclined to go down your technical line. And as for communicating with people of other languages, more than likely your Chinese, your Germans, your Japanese, they're going to be most likely communicating either directly or indirectly themselves in English. Otherwise, you get your tools out and you get someone doing the communications, because unless you're really learning a language really, really well, it is hard to talk at a high level with someone else. Plenty of people those around, but they've gone to university to study papers, another 3 years secondary school, another 3 years at university, and they're usually going towards interpreter roles. They're doing it for languages, for a purpose. I don't know, if that was me, I'd go down that, say, look, I'm technical, I'm here to do technical stuff. That's the line I'm going down. I'm not going to spread myself too thin. If I need assistance for something else that's peripheral, like a language, then I will get assistance for that. That would be my take.
all right.
So Chris,
Thanks.
do you want to just press stop on the record button there?
Oh, yes. Yep. Now, where is the record button gone? Okay. We can... No, it's gone. It might be under more. No, stop
Anyway.
recording. Aha. Stop.
Thanks,
Okay.
Chris.
Yeah, no, so I hope that answers